Thank you. Thank you all for coming. Let's talk about taming the beast, the RISC-V verification challenges. So I'm going to talk about how formal verification has made life easier in tackling bugs. So a brief insight into who we are. So I founded Axiomise in 2018. So the idea was to make everybody empowered in the use of formal, so enable predictable formal verification for all. So the idea was to make all chip design engineers enjoy formal, make everyone adept. And the idea is so you can avoid bugs and detect them and erase them and prove bug absence, the holy grail of verification, tape out without any bugs. So how are we accomplishing our vision? So we have a four-way solution to tackle the challenges that we see in the industry. So if you've got teams of people who need upskilling in formal, we can offer training. If you haven't got the teams of people and they're busy doing UVM, we could come in and actually conduct the work ourselves using the consulting and services model. And if you haven't got time, because it is going to take us some time to carry out the verification for certain custom domains such as RISC-V, we've built an app which can actually verify your processors architecturally. So whether you are in here for a RISC-V oriented view of the world, or whether you actually build a lot of other chipsets which are not dependent on RISC-V, we may be able to help you. So our core expertise is in consulting and services, and if you have touched or you touch any of these devices that you see, AI/ML accelerator, Ethernet switches, mixed signal low power chip, if any of these design components, IPs, whatever you want to call them, if they cause you headache, then it's something we can do to make it easier with formal. This is not an exhaustive list of the things we've done, but this is some of the more recent work that we have been doing. It doesn't matter whether you are a GPU vendor or a processor vendor or a networking chip vendor. If we can all use Verilog and VHDL to design these things, we can use a common methodology base to verify it in formal. It's possible, we are doing it. Some of the happy customers who were happy to say what we did, but were not happy for us to share their names, they're here. Thanks to them. Thanks to Rick O'Connor, Open Hardware Group, President and CEO. We have engaged with the open source community to carry out some of the work. I'll be talking about that today. But a lot of the work we do is non-RISC-V based, and wherever we have gone in, it is an interesting journey. You have teams of experienced people doing formal for a number of years, in some cases new people, and we've been able to make a valuable contribution to their problems. That's the moral of this slide. Verification. So let's talk about what happens when we get it wrong. So anybody remember any of these events? If not, then it's a gentle introduction. So FDIF, Intel had to sadly replace every Pentium on the planet at the time, but since then ramped up a lot of effort in formal verification and has been on the cutting edge of formal verification deployment. Ariane 5 blew up in air because somebody forgot to test overflow and typecasting type issues. Anybody heard of Meltdown, Spectre, or Pac-Man recently? I'm not saying with formal verification we can solve all your problems, but there's a high likelihood that we might be able to avoid some of your future problems. It is all about asking the right question. So why is processor verification hard? Because it's not just functional verification. We need a holistic approach, which is currently missing from verification. The whole industry is dominated by simulation, and whatever is not done by simulation is done by emulation. And where we are kind of missing the trick is we are looking at these problems as simulation-oriented or emulation-oriented, and now I get asked whether it is formal-oriented. I think we're diving into technology space much too soon, and what we need to do is to take a step back and look at the whole gamut of how do we go from architecture to silicon. And what are those verification concerns that we would be worried about, whether they would be architectural or micro-architectural? These Venn diagrams that you see on the slide are representative of the overlapping verification impact of one bug on the other one. The sizes are not indicating that lockstep is bigger or power is bigger. What happens is when we looked at a number of RISC-V designs, as an example, we looked at X issues that were causing issues on the output pins. They were there to save power, but then they were also causing the processor to not have lockstep behavior and additionally cause lockups. Security was another aspect I'll briefly touch upon in one of the slides. Everything is important. The architectural spec-based verification as well as focus on the micro-architectural challenges is equally important. We need to look at the whole lot, not just a part of it. And formal verification is great for everything that you see on this slide. I may not have time to go through all the details today. Modern day processors have got a number of optimizations. I mean, you guys would already be aware, pipelining, interlocking, forwarding, branches, jumps, exceptions, stalls, interrupts, debug. I can go on and on. Extensions, especially in the context of RISC-V, clock gating, arithmetic, power-based analysis, safety, security, heavily optimized. It's basically the optimization in design that causes a lot of headache for verification. I mean, conceptually, a processor is a very simple device, but it becomes very, very complex when micro-architects and architects do this kind of optimization. So why do bugs escape to silicon? So I think, as I said, simulation is the main workhorse. I don't think anybody would disagree. By definition, UVM is stimulus-oriented. A lot of the effort in verification is spent in driving stimulus and conceiving these scenarios, which can then drive the chip to exhibit any of these bugs. So the problem is there are too many dependency scenarios to cover exhaustively. Conventional verification, of course, relies heavily on architectural testing way before even UVM was born. Intel and IBM were making processors and testing them using directed test, unit-level testing. UVM randomized testing, the main de facto verification paradigm today. Unit-level testing is good for bring-up testing, but isn't comprehensive. Randomized testing can reveal corner case issues, but is not exhaustive. Okay, so we have two different technologies for verification. Both of them are inadequate in their own ways. Bug escapes are inevitable. Now, I'm not saying if you use formal, you can never miss a bug. The likelihood of missing the bug would be greatly reduced. That's what I'm saying. So, too many dependencies scenarios. So, for example, do interleaved instruction sequences always work as expected? For even a small core, we are talking about 32 registers, say 60 plus user instructions. The space is huge. Think about a very simple optimization data forwarding in a pipeline processor. How many instruction combinations are you going to test to see that all operand values have been tested against all possible instruction interleavings? You'll be sitting there forever, right? So let's look at a more complex control and data dependency scenario when you have speculative branches, forward jumps, backward jumps, page size jumps, page boundary jumps, all of these different scenarios for which you'll write your functional coverage specifications and test this in UVM or even directed tests, jumps across pages. When you're building load store units, you're thinking about caches and how the transactions from the core to the main memory traverse through different memory hierarchy. So you're talking about write-through, but also cache hits and misses, tracking outstanding cache transactions, bypasses, atomics, the topic of cache coherency. It's not easy to actually dream and visualize all possible combinations of stimulus patterns that you can inject to find these bugs. So imagine a load instruction trying to load data from this address location into X1, followed by an add instruction, followed by another load that actually references the same register for address calculation and moves the data to X1. Now, what if the second load was issued out of order with respect to the first load? If this does happen, then the second load will update the value of X1 incorrectly, causing the value of X1 to be passed incorrectly to the add instruction. This is a very simple program. When you write it down like that, you say, oh yeah, of course, this isn't going to happen. The trouble is you might have atomics in the middle, you might have stalls, you might have interrupts, whole lot of stuff might be going on which you may not be able to visualize. How many test cases would you write to check this case properly? How many random tests would you run to check this? So when things get really hard, talking about the RISC-V weak memory model, there are 13 axioms in the weak memory model specification written by the foundation. Some bugs were caught by academics in Princeton University. We've been looking at these memory models for our work for RISC-V. And when things get really hard, I like to lean on higher order logic, which is what you see on this slide in this little diagram. And if you do find it hard to understand, I can break it down, but basically what we're saying is that we are issuing two stores, not necessarily back to back, but we are issuing them to the same address location to which we're issuing a load later on, and we would like the load to pick up the value of the latest store. So in plain English, that's what we are trying to say. In higher order logic, we would say like that. We could do reasoning not just about the load value axiom, but all of the fence descriptions and all of the other instructions in the RISC-V specification. But what we will do then is in the SVA world, which is the world that a lot of people in the industry understand, is write an assertion that says that no matter when you issue a load word, for example, byte aligned, word aligned, you could then get the data to reflect in the registers that you care about, which were actually the ones described in the issue stage. And when we verify an SVA property like that in a formal tool like Jasper Gold, for example, all possible instructions, including all variations of loads and stores, are interleaved with the issue of the load word instruction. So if there is a bug that is going to manifest due to any problem, you are bound to catch this. We don't have to do anything to drive any particular specific combination of load or store or add or offense. All we do is model these properties and run them in a great tool like Cadence's Jasper Gold, and we run with it. And we run with it so that you don't have to go and write these tests anymore, right? That is what we are trying to make it easier. This is why I say we are trying to tame the beast. If you don't want to actually understand the higher order logic, then it's fine. You can work with the property set and you can still save your time. So can it actually make a difference? I can talk the talk, but can I walk the walk? So here are some of the results from deploying our formal verification app on numerous open source cores from 2019 to as late as 2021. And you will see in a number of cases these cores were verified previously by simulation, in some cases simulation and formal. And some of them were really small, like IBEX and Zero RISC-V with 2 stages, and 4-stage CV32E40P, in-order core embedded class. This was a 6-stage in-order pipe. We don't actually see any performance issues with proof convergence, with coverage. I've done a lot of talks on this particular topic. I would encourage you to go on our YouTube channel and look at a webinar I did with Cadence last year, which describes a lot of detail on coverage and other such items. So yeah, Ashish can do a 32-bit core, but surely Ashish 64-bit core don't work. 64-bit is really hard. Oh no, we did WARP5, that was 64-bit in order. Oh, you can do in order, but you can't actually do out of order, can you? No, we can actually do in order, we could do out of order, we can do multi-threading. It's the technology is ready. So these are some of the results we shared last year in the webinar for CV32E40P. It's a 4-stage embedded in order core. And this is some of the work we recently did on CVA6, which is a 64-bit 6-stage out-of-order core. And the runtimes have certainly increased. There's no doubt about it. Some of the proofs are now running for hours, as much as 60 hours, but they still prove. We've thrown a huge machine. This is being done on a very RAM-heavy 28-core compute cluster, and this was the only job running on it. I didn't have to multiplex it with any other compute load. But it's been hours of fun trying to crack this one. You have a reorder buffer type unit in here where instructions sit and wait for dependencies to be resolved. It's it's a very advanced core with MMU as well. It's not multi-threaded yet. So I'm sure when things get harder, we'll find some other ways. So this is a really quick example to show you what happens when we actually run formal on a core. So this is IBEX, week 1 of development. Designers asked me, said, you just done work on zero risky. Could you just check out and see what your app finds? I set it up in the app, get up to boil some water in the kettle for a cup of tea. By the time the tea is made, all the instruction properties had failed. All of them had this interesting looking scenario where if you had, so if you have a scenario where your controller FSM is in decode state and this debug arrived in the cycle that the state machine is in decode state, then all hell will break loose. None of your user instructions other than 3 shift instructions would work correctly. I actually went on to prove that actually if the state was any other state, if when the debug arrived, would it affect? Actually, no, the processor works correctly as expected. It is only when you are in this particular decode state. I mean, this is a very small pipeline, 2 pipeline stages deep. There isn't any redundancy of storage units and so on. So, I mean, it is week 1 of development. What surprised me was it was a clone of Zero Risky, so I wasn't expecting things to have changed that much that quickly. But apparently it was still under development. So there was nothing in the design to have taken care of those aspects. I could do a diff with Zero Risky and could nail it down. I could see in Jasper, it said, we need to rewrite this thing. The point is, even when I'm in my week 1 of development, I don't need to go write a test case, right? I just can go make myself a cup of tea, right? Let it run. How long does it take? I mean, imagine trying to write a stimulus, apparatus, do all of this UVM business just to catch this little bug, right, in a two-stage pipeline processor. Come and tell me honestly, how long would it take you to do this if you had not done this before, new development? It took 7 seconds, right? So this is an interesting one. This is a load instruction on Zero Risky not working correctly. What has happened was, by accident, the developers of Zero Risky had left a custom instruction from Risky into the Zero Risky design. Now, as a result, the load instruction was not working as per the RISC-V spec because the reg load was superseding the normal memory, load from memory instruction. And again, it was really no effort. Jasper found the bug trace very quickly and we could correct it, and the designers, by the way, everything that I'm saying here is on GitHub. I think I've forgotten to put the link in here, but you can Google for these things. The description of the tickets and the trace is all there. This is Warp 5, previously formally verified by another team. When we picked it up, we found lots of issues. Some of them are really juicy, interesting ones, because when Steve Hoover built this, his understanding of the spec was not fully well-formed. So he was relying on the Symbiosis team, who had also built the RISC-V formal solution at the time. And Steve said, I just went and looked at what they did, and I copied that in the design. So therefore, their interpretation of how you interpret the branch instructions is not conforming to the RISC-V spec. And that happened because in this case, common mode issues can happen if you're not careful and you rely on another's model and you trust that model. I'm not saying you trust our model either, but our model has been applied on numerous cores. It has been derived from a formal model. We have high confidence that our interpretation of the RISC-V specification is loyal. But the problem is, if you aren't a formal savvy person or you haven't got teams of people and you're building a RISC-V based chip and you want to get it to the market free from any defects, then we have something which can help you get there faster and more exhaustively. So we call it formalISA, and we built this because we are aware about the challenges that come with formal verification adoption, the learning curve, the proof convergence issues, writing efficiently, I run a whole training program on this and I train customers. There's even an online cloud-based program called formal verification 101 that you can do in your own time. We are doing everything we can, but not everybody has the time and the resources to do the training. So I said, okay, let us build a custom solution targeted for RISC-V. So the way this works is, this is the RISC-V ISA, and what we did was, we did the formal model development and coded this all in system Verilog assertions. This then goes through a setup phase with the design. So the design signals that are mirroring the architectural signals, your program counters, register signals, your load store unit interface, your CSR signal names, we map them. And after the mapping phase, we throw the customized unit into a formal tool, in this case, Cadence Jasper Gold, for example, and you get a dashboard like that, or you get a trace like that. We are completely vendor neutral. You can use any formal tool you like. We heavily use Jasper for numerous reasons, but also because we found it to be often faster for RISC-V designs. So the point of this RISC-V solution is that you wouldn't have to write a single test case. Your 10-year-old son or daughter should be able to start the app and get your results, run overnight, debug reports generated, coverage dashboards generated, no manual checker to write, no verification code to be written. Harness the power of exhaustive formal, that all ISA instructions work as expected under all conditions. I beg you to please do not waste time dreaming of crazy stimulus. You're never going to be able to find all the stimulus patterns, especially when the cores are complex. Believe me, if you're building an out-of-order core, you're building a weak memory model, you're going to have bugs if you're only banking your bugs with UVM or unit level testing. So all I can say is, don't do this in your own interest. What goes in your app is your RISC-V core setup file and a coverage spec. I haven't got time today to walk through the coverage spec, but the webinar I spoke about with Cadence has got a lot of details. So you can exhaustively prove under all conditions that instruction in the ISAs work as expected. Scenario coverage is a functional coverage-like methodology where I can generate automatically specific instances of scenarios which you specify in a spreadsheet and press a button, cover, and it generates a whole lot of properties. And they are then proven as asserts and covers, which you can then take to your management or to an architect and say, hey, here is what I actually proved. You don't have to then say, we are a formal guy, we proved it exhaustively. What did you actually prove? We proved that this is specific interleaving is working correctly as well. Is there anything else that is of interest to you? Let us know, we will generate a scenario. So this is where actually you want to talk a language which the rest of the community understands. So the way we run this literally is through this RTL setup phase and go and press the buttons in the app. I'm happy to give you a demo. We can set up a call later on. I can show you how this is done. When we were doing work for CV32E40P design, we were literally just doing it like this. We are a small organization. I haven't got 1,000 people in Axiomise. When I was doing all of this, I was by myself. So while this was running, I was doing other stuff. It's all about efficiency. And why you should use it is because it's a push button GUI base. It will save you hours of time. How many hours do you burn writing a make file and inheriting someone else's flow with the wrong switches and God knows what, right? So you can efficiently find bugs without writing any tests, exhaustively prove the compliance, visualize these behaviors, and basically the whole thing is agile, right? So you don't have to wait for your design to be finished. If you've only got a new core where you're adding a bunch of new instructions, you can only focus on those ones. This is a very much plug and play infrastructure. It's not like you have to run the whole lot before you find the answers to the ones that you're looking for. Get predictable runtimes. If the runtimes are not predictable, then I've got work to do, which we do. But we are trying to take a problem that is inherently NP complete and super exponential, and we're trying to make it run in linear time. So the challenge is all on methodology, and this is where we try to focus a lot of the work. You could focus on functional safety and expose security Trojans, and use ISA coverage analyzer for sign-off. But if you don't trust the ISA coverage analyzers, we have a 6-dimensional coverage methodology. And this is like a heat map in terms of how you go about in a progressive way by identifying the coverage targets for the full process of verification, formulating it as assertion properties, doing the checker analysis for completeness, over-constraint analysis, using the tool-based switches for checker coverage, mutation coverage, and stimuli, and then lastly running the scenario coverage. This is a methodology that we are now deploying on numerous customer-based businesses that we are doing, which is not RISC-V necessarily, and it's not something that is only RISC-V specific in any way. So we have built the industry's first and only end-to-end vendor-neutral formal verification solution for RISC-V. You can verify compliance if that's what you care about, but you could go the full hog and do the whole lot of verification exhaustively. In the past, this thing has been tested with multiple tools. You can verify beyond doubt with formaliZer. So bugs are a natural consequence of design, and bugs caught late in the design result in very expensive fixes and catastrophic failures. Formal would enable efficient bug hunting and exhaustive proofs right at the time of design bring-up. My anecdote about the IBEX story. Architectural validation must employ formal verification to build proofs of bug absence. Architects can use this, designers can use this, verification engineers can use it. You don't need to be an FV expert, you don't need to be a PhD. You can learn more, we can teach you if you wanted to, but if you don't have the bandwidth, you can run with this today. Find bugs, I would say, build proofs, and obtain interoperable coverage models for use in simulation and other formal tools. And use any formal verification tool of your choice. I'm not selling you that you have to use Cadence. I'm standing here at the Cadence Theater, right? There are multiple reasons why we use it. One of them is performance and proof convergence. And we find that on RISC-V based designs, it's hard to beat Jasper. it's the truth and an honest truth. So, and I'm happy to take any questions.
So do we have any questions for Ashish? Yeah?
Yes.
Go ahead.
Could you come forward a bit?
Yeah, please. I'm sorry. I think we...
Yes. Yes. You mean in the memory sense, yeah? So the question is, can we actually validate write after write optimizations? Oh. Yeah. 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 So when we are running an architectural check, we actually do not care about your optimizations. We don't even know what you've done. I have no idea what CVA6 does internally. I've never looked at the RTL myself. We didn't have to. What we really care about is that your instructions like loads and the register-based instructions, they have a very precise semantics. It should all map down to our property set, and that should not fail. If that fails, it could be for two reasons. Either we have a setup issue where we have mapped the wrong signals, which is usually easily resolvable in a few days, in the worst case. But if not, it has to be a design issue or an interpretation issue about the RISC-V spec, which has also been the case. So in particular, when we are running an architectural app, we are not really specifically looking to verify a specific optimization through the architectural properties. But if you were to specify the scenario that you're just describing to me, I could write a spreadsheet entry and it will convert that into an assertion and a cover. And that can then be used to validate that specific optimization scenario, which we can then bring it to you and say, hey, is that what you were really worried about? And this is how it works. So the real fun happens when we can work closely with architects and designers who can specify all these scenarios for us. I mean, we do what we do from how we know the processor domain, but architects or micro-architects are wizards, right? They have more idea about what specific scenarios they're looking at. I am not saying that we will not encounter more problems with proof convergence and complexity as we move on to multi-threaded cores or multi-cores. And it is not just a core verification problem. The work we are doing with the load store unit actually is a direct interface to the memory via the cache subsystem. So if you have a multi-threaded core which is actually operating on shared memory, we're going to catch those bugs. See what I'm saying? So although we are not doing a cache subsystem verification target, we are only interested in verifying the architectural payload of load and stores working correctly and all of the atomics and so on. So yeah, it is a little difficult to conceive, because it is so high level. Every instruction in the RISC-V ISA has got to be mapped to a property. Or more, actually. It doesn't have to be just one single property. For loads and stores, we have tons of properties, byte align, misalign, exceptions. I just showed you one example for a simple case. Any other questions?